Hello, James again. This is problem 3 of homework 6, and you see the problem there at the top. To start to solve it, I'm going to draw the circuit because otherwise the problem would be impossible to think through. I have to keep track of things like the directions of currents through circuit elements. So I'm going to draw a big picture because it will turn out to be much better. And I say this out loud because my inclination is always to draw a small picture. I suppose I'm stingy. And so we have the battery on the left, and we have resistors, and we have a battery on the right. And another resistor. Okay. And this is battery 1. This is battery 2. We have resistor 1, resistor 2, and resistor 3. Okay. Now, this setup is not amenable to solution by means of replacement with equivalent resistances because we have more than one battery, that there's no part of the circuit that's purely in series or purely in parallel. So we're going to solve it using Kirchhoff's laws. And first one is the junction rule. It says that the current in equals the current out, or the sum of currents in equals the sum of currents out. And we have two junctions. They're going to give dependent equations, so only one of them will be useful to us. I'm going to talk about this junction, and I'm going to choose the current in the left half of the circuit to be going clockwise. So it's going to be going this way into the junction. I'm just choosing that as long as I'm consistent with my signs, it doesn't matter which way I choose the current to be going in the beginning. If I choose it in the wrong direction, I will get a minus sign, and that'll tell me which way it's actually going. So current 1 is going into the junction up here. That means that it's going through resistor 2 to the left and through battery 1 up. See, it's going clockwise. On the right, I'll choose the current again to be going clockwise. If you compare this to Professor Ernst's solution, you'll see that I believe he chose the current to be I2 to be going in the other direction. You'll see that a minus sign arises, which tells us that I2 actually does go to the left at the top. So I2 is going clockwise, meaning it's going down through battery 2. It's going to the left through resistor 3. And there's a current in the middle part that's different in general from the other two because you have a junction here in order to get to the middle part. So I'll choose that to be going down. And if I write out this equation, given my choices, then at this junction I have I1 coming in, and I have I2 and I3 going out, so the total going out is I2 plus I3. And that's the first equation. So what we're going to do is we're going to solve for the currents and use them to find the voltages. Okay, so we need 3 equations to solve for 3 currents. The other 2 equations we're going to get from the loop rule, which says that the sum voltage changes around a closed loop is equal to 0. And I'm going to choose, there are 3 loops I could look at. There's the left loop, the right loop, and the outer loop. Only 2 of them will be independent, so I can choose any 2 to solve the problem. I'll start with the left loop. And so if I go around it clockwise, which is another choice, I could go around it counterclockwise. It would just introduce an overall minus sign, which wouldn't change my answer at all. So it doesn't matter. I'll go around it clockwise. So I go through resistor 1 down, which is the direction of current 3, through resistor 1. So I get a minus I3 R1. If you go through the resistor in the direction of the current, the voltage change is negative. If you go through the resistor in the direction opposite to the current, the voltage change is positive. So if I had gone up, I would have had a plus here. So I'm going down, I'm continuing clockwise. I go through resistor 2 in the direction of current 1, so it's minus I1 R2. And I go through battery 1 from negative to positive, so it's plus V1. And then I come back to where I started, so that whole thing equals 0. If you go through the battery from negative to positive, the voltage change is positive because the current is gaining energy from the battery. Okay, that's my second equation. And my third equation, I'm going to choose the right loop. I could do the outer loop. It doesn't matter. So going around the right loop clockwise, again, a choice. I go through battery 2 from positive to negative, which means I get a minus V2 because I'm going in the direction that charges the battery. So I go through resistor 3 in the direction of the current, so that's a minus I2 R3, which is the voltage IR from Ohm's law. And I continue clockwise. I go through R1 in the direction against the current, so it's going to be a plus I3 R1 equals 0, and that's my third equation. All right, now I do algebra. So the answers you would get are, let's see, you get I1 is 4 times 10 to the negative 4 amps. I2 is negative 2 times 10 to the negative 4 amps, which is minus Professor Ernst's answer. It's because he chose I2 to be going left, and I chose it to be going right at the top. And I3, you get 6 times 10 to the negative 4 amps. And then to answer the question, what is the voltage across each resistor? For example, you get for R1, V for R1 is going to be I3, which is the current through R1, times R1, which is equal to the 6 times 10 to the negative 4 amps times R1, which is 2,000 ohms, which comes out to be 1.2 volts. And similarly for the other two, VR2 is going to be the current through resistor 2, I1 times R2. I1 is the 4 times 10 to the negative 4 amps times R2 is 1,000 ohms, which gives you 0.4 volts. And R3 has voltage, which is I2, the current through R3 times R3, which is equal to, I'm going to take the absolute value because the minus sign just gives a direction. So it's the 2 times 10 to the negative 4 amps times R3, which is 1,000 ohms. It's given in the diagram in the problem. So that's 0.2 volts. Okay, so that's part A. The answer to the circuit by any of the batteries that are spending energy. There we go. So power supplied by battery 1 is going to be positive. In other words, battery 1 is supplying energy to the circuit because the current I1 is positive and it's the direction in the diagram is from negative to positive. So the positive sign here means that I1 is actually going up, meaning it's going from negative to positive, meaning that battery 1 is supplying energy to the current, to the circuit. So power 1 is a supplied power. The battery 1 is giving energy up. And so we want to solve for that. So it's the current through battery 1, which is I1, times the voltage for battery 1. I1 is the 4 times 10 to the negative 4 amps, times V1 is given in the problem. It's 1.6 volts, which comes out to be 6.4 times 10 to the negative 4 watts. Power 2, again, we only want it if it's positive, if it's supplying, if the battery is supplying energy to the circuit. So I2 in the picture goes from positive to negative, which means that if I2 were actually going this way, battery 2 would be charging. It would be taking energy from the rest of the circuit, not giving energy to the rest of the circuit. But I2 turns out to be negative, meaning that the current through battery 2 is actually going from negative to positive. It's going up in the picture. So battery 2 is supplying energy. And so we want to calculate its power in this part then. So the power is the current through battery 2, which is I2, or absolute value of I2, times V2. So that comes out to be 2 times 10 to the negative 4 amps times the voltage given in the problem for battery 2, 1.4 volts. So that is 2.8 times 10 to the negative 4 watts. Okay. Now, part C, it asks for the total power dissipated by the resistors. Well, you could find the power for each resistor and then add all of those up. But because the only things in the circuit are resistors and batteries, and because both batteries are supplying energy, that means that the power dissipated by the resistors equals the power supplied by the batteries. So the power dissipated is equal to power supplied, because none of that power supplied is going to, for example, charging a battery. All of it is being dissipated in the resistors because energy is conserved, and there's nothing else going on. So it's just power 1 plus power 2 from up here. And so that's 6.4 plus 2.8, which is 9.2 times 10 to the negative 4 watts. And part D, what is the total power stored by any of the batteries that are storing energy? Well, none of the batteries is storing energy. Both of them are supplying energy because both currents are in fact going from the negative side to the positive side of the battery. Remember, I2 is negative, so it actually goes up. So neither battery is supplying energy. Both batteries are supplying energy. Neither battery is storing energy. So the power stored by a battery that's storing energy is 0 because no battery is storing energy. Okay, so thank you for listening, and I'll end that here.